Hi guys, so in previous video we talked about inverse transform sampling, which utilizes the inverse cumulative distribution function ICDF, and we talked that it's really useful for generating numbers or samples from the standard distributions you learn about in your probability lessons, such as normal distribution, such as exponential distribution, such as Poisson distribution, Weibull distribution, beta distribution, gamma distributions, the standard distribution basically. Okay, and in order to use inverse transform sampling, you must explicitly know what the inverse cumulative distribution function looks like. But at the same time, you mentioned that if you have some really ugly distribution, so for example, a distribution with this density function, it's really difficult to obtain the ICDF. Or maybe it's not difficult, but it's just tedious, you don't want to do it. So in these cases, it can be useful to use the rejection sampling. Rejection sampling does not really need ICDF. Only thing it needs is that the density function can be evaluated. Basically, this means that if we have, I don't know, let's say that the function is explog, for example, something like this, that we are computationally able to evaluate it. So if I plug here, I don't know, 1, I get 1. If I plug it something else, I get something else. It's not like I plug it something and I don't know how to actually evaluate it. Okay, so this is the only thing we need in order to employ rejection sampling. So now let's get to the idea behind rejection sampling. So I'll just delete this. I will keep the function here. So the basic idea. We don't know how to sample from this ugly distribution with density function f. So instead of sampling from it, which we don't know how to do, so we cannot do it, we will overlay this f function with some other density function from some distribution we know how to sample from. So let's say that this is, we will call it G, sigma, not sigma. So let's call it G, and let it be a normal distribution, something we can sample from, or uniform distribution, doesn't matter. And now the idea is, so we have this distribution, it's overlaying, meaning the blue line is always above the red line. We can sample from this blue distribution, so let's say that we obtain these samples, I don't know, samples like these. And now we'll look at each sample and we will look at the probability of this sample under the distribution f. So if it seems that the probability of this sample according to f is high, we will accept this sample. And if it seems low, we will reject it. So for example, here, okay, so this x is something right here. Is it low or high? Let's call it low. So we will reject this one. Not. Here it seems, okay, this is high, so we will accept this one. This one is, okay, it's quite high, so we'll accept this one. This one is really low, so no exception here, and here also not. So if we do this enough times, we will get some we will accept some samples, and if we we will have this list of accepted samples, and these will be distributed according to f. Okay, and that's the whole magic. So now the good question is, how do I determine whether the probability of this sample is high or low, right? So here I just randomly set high or low, and in real life we need something like more deterministic, and we will look at it right now. So more sophisticated example. Again, we have this ugly density function that we want to sample from. We don't know how to do it, so we will overlay it with a nice density function we can sample from. So in this case, let's say that the blue line is normal distribution, fx likes the red line is something we want to sample from. So first, we sample from the blue distribution. We do know how to do it. Yes, we can sample from uniform distribution. From normal distribution is no problem. So we sampled from the blue distribution. Now, we draw a line between the sample and the distribution. So, meaning, if this is the gx, this is g, so let's say this is the g at point x, this is the x, right? We draw just the line. And now we will sample uniformly on this line. Okay, so this basically means that, okay, so this is the gx, this is the x, and here we just sampled uniformly from uniform distribution between 0 and gx. Because 0, this is on, if we did here a epsilon y-axis, this is 0 and this is gx. So this is 0, this is gx, and we just choose random point on this line uniformly. And now, if this green cross is above the red line, so let's say this is fx, which it is, we will say reject. So again, if the x, the green x, is above the red line, we will reject the sample. So this sample will say no, reject. If the sample is, if the green cross is below the red line, which means it's less than fx, then we would accept it. And this is the magic. So again, we sampled from the blue distribution. The line, we draw the line. We sampled uniformly on the line. The sample, or the point on the line, is below the fx. Oh, I should use red, but whatever. It's below the red line. What does it mean? Accept. Accept. So we accept this sample. Accept. And again, we sampled from the blue distribution. We draw the line. And now we choose random point on the line. Here's the point. It's well above the red line. Yeah, it's above. So we reject. So this sample, no. Again, another sample, another line, choose the point randomly. It's well above the red line, reject. Another point, draw the line and choose the point randomly. Now it's below the red line, meaning accept. So we accept this point. Again, sample, draw the line, draw some point randomly, and we see that the green cross is well below the red line, meaning accept. And we accept this point. And we repeat this process many times And we, after some number of steps, end up with this. And as you can see, the majority of the samples is concentrated where the probability is high, meaning here this is a high probability, this is also high probability, and here we have some real like leftovers, not that high probability here. And this is the magic. That's it. This is the rejection sampling, the idea behind it. Yes, so this is the array of samples, and we know that it's distributed according to F, according to this distribution. This is the algorithm. So again, we have some ugly function f. So first we choose overlying density. So let's this be the overlying density G. Draw sample from G. Now draw sample from the uniform distribution between 0 and gx, and if it's below the red line, below the fx, accept. If it's above, reject, and repeat this process over and over again. Now it's important to ensure that the G is always overlapping, meaning at each point overlapping the F, because otherwise the algorithm does not work. It would break if we tried to do it. So for example, if our overlying function looked like this, then this algorithm would not work, right? We would sample, we would accept everything because each time this condition is satisfied, and we would accept everything, and we would end up with this distribution in the end. Okay, so this is not what we want. We must ensure that the G is always above F. But how to do it, right? Because maybe we are using the G is a standard normal distribution, so it looks like this, and we don't know how to like push it upwards. So in these cases, we can multiply this standard, and this is standard G. We can multiply it by some number. Let's call it m. So if we multiply by m, then we will move the entire G line above, and suddenly we can we would get this overlying density, and we can do the sampling. This is the trick. We can multiply the overlying density by arbitrary number, and it still works, or we have to do it to get this overlying distribution, but the algorithm still works. And the second thing to note here, we might want to replace this step and this step with here with 0 uniform distribution from 0 to 1, and if we do this, then we have to adjust this as follows: times G, maybe m times G. Yeah, this follows the standard uniform distribution behavior. You can like this, you can get these out in this manner. Okay, so that's the algorithm. That's it. So once again, we have this ugly function. We overlay it with some nice density function. Sample from the density function. That's nice. Draw the line. Choose random point on the line, and if it's below the red line, then accept, and if it's above, reject. So in this case, reject. Good. So pros, it's really straightforward, right? It's very simple. The idea is simple, and the implementation is even simpler. And also, because we do not rely on inverse transform or inverse cumulative distribution function, it's kind of more versatile. We can deal with these ugly, very ugly distributions. But it comes at a price. Let me draw this. So let's say we have this ugly function f. Okay, so it starts somewhere, it's somewhere. And now, oh, sorry. And now, what's the problem? Problem is that we can choose the overlying densities, and we can choose this overlying density, which seems quite fine. But we can also choose quite not fitting overlying densities, or something like this. Now the good question is, what's the difference between these two overlying densities? The answer is that the accept ratio, or the number of samples you will accept, or the probability that you will accept the sample, differs. Because if we sample from this blue distribution, this light blue, so for example, if we sample these samples, or maybe let me draw this in the right colors. I have this, and now let's draw it. Okay, so we sample from the light blue distribution. It's uniform. Then if we draw the line, so we draw this, and this, and this. Now each of this line has, let's say, decent probability that we will accept the sample, right? So here, this is like, let's say that this is like 1/3 of the line is above, 1/3 of the green line is above the red line, and 2/3 of the green line is below the red line. Which means that now we have 2/3 or 0.666 probability that we will accept this sample. Which means that it's quite a nice probability, right? If we sample this particular point, I don't know, 10 times, in 7 cases we would accept it. In 2 cases we would not accept it. On the other hand, let me draw this in blue. If we sampled from this upper distribution, which is also overlying, so it's perfectly fine. It's a very valid choice for the overlying distribution. So let's sample, I don't know, here, 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 and here. Maybe even the points before. Now we draw the lines. So here's the line, here is the line, here is the line. As you can see, now it feels like, I don't know, this feels like 5/6, I don't know how it's pronounced, is above the red line, and only 1/6 is below the red line. And the same thing here, maybe here it's quite different, maybe here we have 1/2 above and 1/2 below, but it doesn't matter. Or maybe here, this is a really good example. So this feels like 4/5, no, it feels like 4/5 are above and 1/5 is below the red line. Now, for this sample and this distribution, you have just 1/5 probability, meaning 0.2 probability that you will accept the sample, right? So if we sampled 10 times, only 2 times you would accept this sample. Whereas if we use this light blue, the probability of accepting is 0.6, here 0.2. So this is the trick. We must find overlying density, but at the same time, if the overlying density is really close to the red F target probability density, meaning the gap, this gap between red and blue, between overlying and the target density, is small, not too wide, then we will have really nice accept ratios. Like we will sample and majority of samples will be accepted and distributed according to F. But when we choose this overlying density not that well, with these high, very big, wide gaps, then the acceptance ratio will be much smaller. So we have to be careful about this. And this is especially true in high dimensions. So we see that if we fail to find suitable overlying distribution in 1D, in 2D this just gets multiplied, right? So if acceptance ratio in 1D was really small, in 2D it will be much smaller, and I'm not talking about 4D or 20D. So overall, the rejection sampling works quite well in 1D, it works quite well in 2D, but when we get higher, when we get like, I don't know, 40D, then it starts to be real inefficient. And it really depends on how wide this gap between the target and the overlying density is. Because if it's really wide, then even 1D will have problems, and if it's wide in 1D and it's even wider in 40D, then you will get crushed. You will run this algorithm 1 billion times and you will accept one sample. Yes, so this is a problem and you have to be very careful about this. Okay, so I think that's it. That's it for this video. In the next video, I want to implement the rejection sampling in Python. So we see how it works in practice. I think it's something you should be excited about. I'm excited about. So thank you for watching and see you next time, guys.